Hi, everyone. In this lecture, I'm going to go over the relationship that I explained before, that the heat capacity at constant pressure for a gas is greater than the heat capacity at constant volume. I said this was always true under some reasonable assumptions, and this is the supplement video where I'm going to prove that. This is going to be a little bit mathematically involved just in terms of the algebra and calculus to follow, so hopefully that doesn't put you off. I guess with that out of the way, let's jump right into it. Now we're going to need what I called a couple of reasonable assumptions, and let me start off the video by talking about those. Going to need some space first. Let's define two different constants. The first is the thermal expansion coefficient. And in fact, I said constants just then, and often these are measured as if they're constants, when in fact we don't know that to be true a priori. So this is going to be the thermal expansion, coefficient. It's usually called alpha, and it's defined to be equal to 1 over v times the partial with respect to t of v at fixed p and n. Good? And the second thing that we care about is the isothermal compressibility. And this is often called beta, and it's defined to be minus 1 over v times the partial with respect to p of v at fixed t and n. Let me go over what each of these is and then talk a little bit about why we expect both of these to be positive. All right, so first for alpha, imagine that we have a gas and we increase its temperature at constant pressure. Somehow we're pumping heat energy into the system, presumably, to increase its temperature. What do we expect to happen? Well, typically the volume in that case will increase. You can just think about that for the ideal gas if you want a concrete example, but this should be true for any gas. And if it is, then this will be positive. Similarly, imagine that we increase the pressure on a gas at constant temperature. Well, increasing the pressure is very likely to make the volume decrease. And if that's the case, then this partial derivative would be negative. The negative sign out here makes beta positive. So that would justify that beta is greater than 0. Okay, fair enough. But why is there this this v factor in the denominator here out front? The answer is that we want alpha and beta to be intensive. We're taking the partial with respect to an intensive variable. So partial t of v is extensive because v is extensive. So the only way to make alpha intensive is to divide by an extensive quantity. So we choose to divide by v here. And we do the same down here. So hopefully this gives some illustration of why we expect both alpha and beta to be positive. And if that's the case, then we can go about this proof. So let's simply work by definition. Remember that CV is equal to T times the partial of S with respect to T while fixing V and N. And CP is equal to T times the partial with respect to T of S while fixing P and N. What we're immediately going to do is rewrite this partial derivative in the coordinate system tvn. So we're going to go from tpn, since there's a tp and n here, to tvn. Okay, and we can do that as follows. So we're going to get dt of t, fixing p and n, times dt of s, fixing v and n, plus partial t of v, fixing p and n, times partial v of s while fixing t and n, plus partial t of n, fixing p and n, partial n of s fixing t and v. Good. And we can reduce this significantly. The partial sub t of n, while fixing n, must be 0, certainly. Meanwhile, the partial with respect to t of t must definitely be 1. Good. And lastly, if we look at this object, it's very closely related to our alpha that we defined up here. In fact, it's exactly alpha times v. So now we can rewrite that line a little bit more clearly. That's t times partial t of s fixing v and n plus alpha t v times the partial with respect to v of s while fixing t and n. Good. Okay, wonderful. So we're almost at a place where we can say something, and the one extra piece of information we need is that this object is exactly what we have here. In other words, this is CV. Okay, so because we have CP on the left-hand side and CV plus some stuff on the right-hand side, if all this stuff is positive, then we know that CP is greater than CV. We argued that alpha is positive. We also know that for a gas system, T is going to be positive and V is going to be positive. So we're really just interested in this object and whether or not it's positive. Let's see if we can drill into that a little bit more. This would be easier actually if I waited a couple of lectures, but I'm not going to do that. I'm just going to push forward. So I'm going to write du is equal to T ds minus P dV plus mu dn. Again, this is our first law. Now, without telling you why I'm going to do this, I'm going to define the quantity F to be equal to U minus Ts. And then let's look at dF. Well, it's going to be du for sure. Then we need to use the Leibniz rule on dTs in order to figure out what that will be. It'll give us minus TdS minus SdT. But now if we plug all of this stuff back in here, we get that ds has a cancellation in it. Or sorry, df has a cancellation in it. This TdS cancels with this TdS here. And we get that df is equal to minus SdT, minus PdV plus mu dn. All right. Now, the reason I said that it might be a little easier if we waited a couple of lectures is because this quantity f is going to be of a lot of interest to us just a couple of lectures down the line. But for now, it's just going to be useful for this one mathematical manipulation. What we're interested in is the partials of f. So notice that the partial with respect to t of f is just going to be whatever is attached to this dt, because remember that the one form's expansion in terms of these basis one forms encodes all of the partials of the function here. Okay, so the partial with respect to t of f while fixing v and n is minus s. Meanwhile, the partial with respect to v of f while fixing t and n is equal to minus p. Okay, now we were interested in the object partial v of s while fixing t and n. If we want to express that in terms of f, we get the following. minus, so we'll say partial V of S fixing T and N is equal to minus the partial of V sub V of the partial sub T of F fixing V and N on the inside and then fixing T and N on the outside. What we're going to want to do is use the fact that partial derivatives commute with each other. In other words, this partial with respect to V followed by this partial with respect to T. I guess I'm talking the way that it's written. In actuality, it's this partial with respect to T followed by this partial with respect to V would be the same as doing it in the opposite order. So this is equal to the partial with respect to T of the partial with respect to V of F while fixing T and N on the inside and while fixing V and N on the outside. And sorry, I forgot my minus sign in here. That's important. The reason that's important is because this object, as we just declared above, is minus P. So the two minus signs cancel. And this just becomes plus the partial with respect to T of P while fixing V and N. Excellent. Okay, the reason that that was useful is that V, T, and P are much more useful quantities to work with when we're doing actual measurements than S is. S is pretty hard to access. Let's rewrite our heat capacity ratio statement here. So we have Cp is equal to Cv plus alpha Vt, and then it was just times this quantity. So we're going to replace that quantity using the line that we just proved with partial T of P fixing V and N. Now we're almost home free. We would like to get this thing in terms of quantities that we know to be positive. And so because we have this mix of things here, we have our T, P, and V, and we'd like to sort of see these in a different order, this is going to be the first time that we're going to want to use the triple product rule. So let's go ahead and do it. The partial sub T of P fixing V and N times, so we'll move everything to the left, and then if something is on the very left, we'll move it all the way to the right. So times the partial with respect to P of V fixing T and N times, so now P is going to get moved to the right, V is going to get moved down. The partial with respect to V of T while fixing P and N is equal to minus 1. This is the thing we know, so let's get it on a side by itself by moving both of those over. So the partial with respect to T of P while fixing V and N is equal to the partial with respect to P of V fixing T and N multiplicative inverse times the partial with respect to V of T fixing P and N multiplicative inverse, and I forgot this minus sign here from the minus 1. Good. And the last thing that we need to do is use the inverse function rule in order to rewrite this term here. So we get minus partial with respect to P of V fixing T and N inverse times the partial with respect to T of V fixing P and N. Excellent. Now we can rewrite these in terms of the quantities that we know. Because this is in the numerator, this is just alpha times V. And then this is in the denominator. And it's in the denominator, minus beta times V. In other words, when we cancel everything, this is plus, because these two minus signs cancel, alpha over beta. And at long last, we find Cp is equal to Cv plus alpha squared over beta times V times T. Good. Okay, so this finishes the proof. Because all of these quantities are positive, that implies that Cp is greater than Cv under the assumptions that we made. But more than that, I hope that this video helped to illustrate why we spent so long developing the formalism that we did. Because the kinds of manipulations that we're doing here are really pretty accessible in the language and notation that we've developed, but would have been really hard to carry out with maybe some of the techniques that you've seen in the past. And without further ado, that brings us to the conclusion of the video. Thanks so much for watching, and I'll see you in the next one.